Hello, so today we are talking about recursive functions, the part two of this topic 9. So this is not the easiest part of the course. It's pretty hard, so bear with me, and we're going to try to make sense of all that as much as we can in this little rundown video. So let's just recapitulate what we talked about last time. We talked about primitive recursive functions. And primitive recursive functions are basically contain the initial functions, the 0, basically, right? 0 of x equals 0. You have the successor function, the +1 if you want. And we have the identity or projection function. And so these are the initial functions, and then the set of recursive functions is closed under composition. And for the details, you can look at the previous video, and also, the primitive recursion scheme, as we saw last time with the base case and the inductive case. So, so that's basically primitive recursive functions. We saw that it is quite powerful. You can define a lot of things with it. A lot of operations, addition, multiplication, the minimum. You could define, the mean, the variance, all kind of concepts of arithmetic, statistics. So many things can be defined with just this very basic set of functions called primitive functions, with as a starting point, really only the notion of 0 and successor, whereas very, very basic primitive notions. So this is a quite powerful theory. But we make the distinction between the set of primitive recursive function, right? And the set of recursive functions, that is a proper superset of the primitive recursive functions, recursive. And then, as we'll see later, there's a larger set called recursively enumerable functions. And it should remind you of something interesting, is that recursively enumerable is another definition of what we call Turing recognizable languages, and recursive is another term for decidable languages, right? So whatever is recursive is decidable, whatever is recursively enumerable is recognizable by a Turing machine. But we'll make the connection later. Let's stay in the functions for now. There is something missing. So this really defines this set. There's something missing if we want to talk about recursive functions in general, right? So there's a larger, more powerful set, and for that we need the notion of minimization. But it can look a little bit strange, because usually when it's introduced in books or anything, it's just given like that. Oh, you can add to this, you can add mu-recursion, or also called minimization. And we define that as a recursive function, and you get, if you add this, if you say that closed under, right, if it's closed under, so I should actually, to be more precise, I should put it sorry about that. I should put it here. Here. If I add mu-recursion, close under mu-recursion or minimization, then I have now the set of recursive functions. Right here, it's primitive, recursive, and now recursive. Okay, so it looks sometimes a bit arbitrary. There's different ways of defining mu-recursion or minimization. The function is pretty simple. Understanding what does it have to do with recursion, right? Pretty much everything here is straightforward. We saw last time why we have that. It makes sense that we have a starting point, we have an incrementing point, and then we have the capability to have multiple arguments. We could do without it using a process called currification. We could just do with just one argument, but it would make the writing very, very complex and heavy. So this is more of a convenience. We have the capacity to do composition, and this seems obvious that recursivity needs composition of function. It's kind of included in the notion of, and there is a recursivity itself containing the base case and the inductive case. So it's pretty straightforward. Why minimization, right? We could see we could be a bit puzzled by that. And let me just first state what it is. Minimization is the mu recursion that is also called sometimes the mu reduction is such that mu y applied to a certain g x y is the minimum y such that gxy equals 0, right? So, sorry, this are actually regular parentheses here. So, it's pretty simple. You just take the predicate, can be a predicate of function, a recursive function, the recursive predicate g here, and you look for the y such that g of x equals 0, and you take just the first y that makes g of x equals 0. So you have different ways of formulating it. The way it is proposed in the notes, let me find that. It's defined as f of x equals uy equals 0. And the way it's proposed in the book is mf of x equals the mean of y such that fxy equals 0. So these are all equivalent definitions, but we'll see more of this way of this formalism in the theorem that we'll spend some time on in the end. So we're mostly going to focus on that. Basically, the idea is that this is a recursive function, right? So the function on top of that, we can call it x. X. That is defined such that f of x equals mu y g of xy is a recursive function. So we're adding this to the list of recursive function. All we're saying is that f of x is such that it's going to be equal to the value, the first value y, the smallest value y, okay, the minimum value y, that satisfies this condition, such that g of x, y is equal to 0, right? So here there is only one argument. You could have n arguments, right? So f is of arity n, and g is going to be of arity n plus 1, okay? So f of x is not g of x, right? Let's be careful. It's not g of x. It's really the value of, it's not g of xy, it's the value of y, the first value of y that satisfies g of xy equals 0. Okay, so just a little bit of what does it have to do with the rest of these? That seem fairly straightforward. And let me try to give you a sense of it, even though we're not gonna like give tons of details. How does recursion and induction work? As we said, we have the base case, 0. And we show that the function is true for 0 and is true for n plus 1, for any n, right? So if it's true for 0 and for any n it's true for n plus 1, then it's true for 0, 1, 2, 3, and it goes on, right? Without ever stopping. Everything here is defined in terms of that. And we can define, as we saw, functions on top of functions, right? We start with 0, but we can build up functions more and more complex. But we always have this pattern, this picture, if you want, of a starting point and induction forever. Right? Okay. And again, that's the power of recursion. Now, what is missing here in terms of power, expressive power, or computational power of primitive recursive function, is a capacity to know where it stops working, where it starts going wrong, right? Or where it starts going right. If this is true, then that's fine. But some patterns are. This is not always true, and we can find functions for which that are not recursive functions, but we still want to be able to relate them to recursive functions. So how can we do that? Well, we can say if this is not true, if for some kind of function or computation this doesn't hold, then what happens? Then the negation is true. The negation is there is a place somewhere y where it's true before y, but it's not after. Y is a place where these things start going wrong, where somehow the recursion doesn't hold anymore, and it just breaks everything. Instead of not being able to talk about it's right until y, just because it's not after y, we introduce this notion of what is the least number where, what is the limit? What is the point where things start going wrong or start going right? Because you can see things either going like that, but you can see the complement of the function, and it will be like that, right? So you can see it both ways. And usually, actually, because we're looking at the negation of the predicate, it's more like that. So what we're saying is y again is the smallest number that satisfies g is wrong, which makes this the smallest place where things are true, where this is true, the fact that g doesn't hold anymore, g of x doesn't hold anymore. Okay, so we're just saying that in our recursion schema, we're now adding the capability to see a starting point or an ending point for the recursion. So 0 is not our only anchor in some sense anymore. We can start somewhere else, or we can end. I mean, we can start from 0 and end somewhere to y, or start from y. That's the basic idea. We add here something very powerful. It's basically a search capability, right? Trying to think of some kind of analogy. It's like being able to put a cursor in a database, right? Before we had the ability to have the database fill itself automatically forever, but we didn't have the capability to search through it, to read a certain line. Here we have the capability to actually search and point at some specific place. And so that increased considerably the computing power. There's only this one additional recursion function, recursive function in our model increased a lot the computational power and brings us actually very close to what we consider to be a Turing machine, right? Okay, so now for the tricky part, the normal form theorem, Kleene theorem. It looks like something very heterodox, very complicated to grasp, but it's not as much as it looks like. And so we've just seen the unbounded minimization because we're going to need it for the normal form theorem. We cannot express it without that. So here is what the theorem says. Take function h. And for the sake of simplicity, I'm going to assume arity of 1 for h, but you could have an arity of n, of course. H of x. H applied to x is going to be equal to another function, another recursive function, right? So we're going to be able to associate always any recursive function with an equivalent recursive function that has some kind of enumeration capability. Enumeration means number index, right? And so here is what's going on. For this recursive function, recursive, there is a number e such that h of x is going to be associated with another function that takes this number, which is the index of the function x, as an argument. So we're going to associate h is associated with a certain number e. I'm going to call it e of h just to see clearly that this number is a connection between h and e. And here is the normal form theorem, is that h of x equals a certain function u of the unbounded minimization of another function t of e x y. Okay, so what are we saying here? We are putting together, we're connecting, in some sense, h with its e number, right? E of h. putting them together. And we're building a function. We're building here a function, a recursive function. U is recursive, T is recursive, and of course the recursion, the mu-recursion, the minimization over T is also recursive by definition. So all of this is recursive. We're building a recursive function that can take as argument the encoded number associated with H. So a function H is now possibly the argument of a function. Well, you could say, well, yeah, we can already do composition of function, but it's not the same thing. Here we're not just composing, right? It's not like the same, it's not like saying, well, H is equal to something composed, a composition of H, right? It's really like, it's kind of like saying, and I'm going to write that just for the sake of understanding, but it's like mathematical heresy. So please, I'm going to use something I can erase. It's kind of like saying, in some sense, h of x equals a special function m that takes h and x. H becomes a number, right? So you have in recursive function you have two realms, right? You have the realms of numbers and the realms of function, the realm of functions, right? The two are not mixed, right? You either basically in recursive functions, you either in the you know, these are if this is the recursive world, and I'm saying world because it's not a set here, right? I'm talking about all the things that make up that you have in the recursive theory, right? You have items, you have symbols. These symbols can be in two categories. Either they are functions or they are numbers, right? Natural numbers. Here, and h is one of these, right? And x is one of these. Here we're kind of doing a trick such that we're putting x into this, and we're finding a special number. So it's not h, and this is why I say it's heresy, right? H cannot be an argument. It's a function. It cannot be an argument. It's not a variable, right? So that's not right. But instead of writing h, we found a special e that is associated with h. We associate h with e, right? We give h a number, right? And so that's my e of h here. Well, it's not enough to give h a number, right? I can say, oh, okay, the function, let's say the function s, I'm going to give it the number 1. Okay, so I can say, oh, s is going to be associated to 1, right? 1 is going to be e of s. That's great. Why not? Sure, but what are you going to do with that, right? If 1 is not meaningful, if there is no way to decode that, right? So you have your encoding that's going to associate h with eh, but if you want to retrieve h from eh and know what eh means, you need to have a meaningful encoding, an encoding that actually can be decoded, and so in such a way that you can retrieve the meaning of h and potentially apply it to arguments. So e of h is not just an index for, it's an index for h that is built in such a way that you have associated with it a certain predicates that can attach this index to arguments and to outcome the results of I mean the actual behavior of h on the arguments. So you have here a triple of e of h, the argument and the outcome of the argument, and we're going to call that y, that needs to be connected together through a certain predicate, and this predicate is going to be t here. T is going to take e, x, and y and put them together in some sense, associate e with x and with y, in such a way that only under certain condition can you say that y is the result of applying e to x, right? If you apply h to x, some specific things happen. You cannot just do whatever you want, right? Because if our h is s, for instance, well, there's going to be a certain behavior when you apply e to x. You're going to get x plus 1. Well, y needs to encode all of that. Y is basically an encoding. So e is an encoding of the function h. The same way that e encodes the function h, x through t is going to be encoded as the argument, and y is going to be an encoding of e applied to x, and I mean e decomposed into smaller and a whole tree, and that's the idea of the computational tree that you have in the notes. I invite you to look at it for more details. I'm not going to go through the details here; it would be too long. But y contains the whole computational tree, down from all the way down to the most primitive recursive functions. And so y contains the key to compute actually the answer of applying h to x. So t puts all of these together, and only in certain condition can these hold. T is actually a recursive predicate, so it takes value 0 or 1. Because it takes value 0, 1, mu y of t exy is going to compute the smallest y, the smallest computational tree, that is such that that this holds. Well, basically, it's just going to find the first y that answers the question, what is h applied to x? What is h of x? It's going to answer the question, but in the realm of numbers. So t is really, t is a function, but t is the function that, again, holds all of these together to make sense of applying a function to an argument and getting an answer in the realm of numbers, right? So y is going to be here too. So y is actually, well, I should put it here because it's really what t holds together. So t is a function, right? It's not a number, but it is going to hold these together, and that's t that makes it possible. T is really the encoding, the coding decoding, right? It's the encoding. It contains the semantics and the knowledge of how the encoding works of the function, so that you can actually retrieve the behavior of h through eh, and retrieve the answer of eh applies to x through y, the whole computational tree. So I know it's a lot, and it seems pretty complicated, but once you get the idea that h connected to h is connected to e, right? Of course, x is connected to x. It's exactly the same value. Y is really, in some sense, mostly connected to t. I mean, is really the interpretation of all of this in the realm of numbers, right? So all of these are in the realm of numbers, right? It's h of x is a number. The answer is going to be a number, but y is going to be the encoded computational tree. Now, the computational tree gives you the key, right? So once we found it, so the mu-y is going to be the selector, is going to be the one finding. And that's why we need the unbounded minimization here, because it's going to really find it's going to find the answer in some sense. It's the capacity to find the answer to a question. And so it's going to select the right y. But once the y is selected, you could say, oh, we have the answer. Why do we need the u on top of that? Well, because the y is an encoded answer. It contains the whole tree. You need to decode it. You need to decipher it, which can do easily. So you could see u as kind of the inverse, like t is the encoding and u is the decoding. It's not exactly true because e is already encoded. T is more the thing that holds together all the encoded version of the function world into the number world. But u is going to have this function of reading the computational tree, kind of like a Turing machine reads another Turing machine, really, to try to figure out, so what is the answer? Now I have all I need to get the answer. I can compute it. Yeah, so let's talk a little bit about that. Again, what have we done here? We have created a kind of apparatus that allows us to take an entity from the function world realm and to put it into, so we could call that the function, realm, and the number realm, to put it into number. And now that it is a number, it can be itself the argument of a function. So you have now h, a function that becomes the argument of another function, because this is a recursive function. Okay, and this recursive function is really indexed by e, the number of the index of h. Okay, so this should remind you of what we've talked about with decidability, the topic 7. In topic 7, we started to look at Turing machines or languages that contained machines, automata. And this is really what we're doing here, right? N is our language. That's the realm of the languages, right? The languages are here. And these are basically the machines, right? The automata. Well, when we started to have machines encoded into languages so that a Turing machine can read a Turing machine, which the universal Turing machine does, which kind of this does. This is really akin to a universal Turing machine. We now are doing really that's when we started. When we started to do that, that's where we started to see interesting things and also paradoxes and undecidability. And we have exactly the same phenomenon here. And I'm going to try to quickly go through that to give you the gist of it. We've just said, so the idea is to say, well, there is no way we can enumerate all function. So you remember with in decidability, we use diagonalization with Turing machines. We use diagonalization to show that some Turing machines were not recognizable, that you could not sorry, that some languages, excuse me, some languages were not recognizable. We use diagonalization to show that there are some languages that that cannot be recognized by Turing machines. Okay, so here we're going to do the same thing. We're going to say to use diagonalization, exactly the same process, to show that some functions are computable or expressible, but they are not recursively enumerable. And so you cannot enumerate all recursive functions. Okay, so here is the idea. Take the following function: g of x equals phi fx of x plus 1. And this is in the notes as well. Sorry, I forgot to define phi first. We assume that we can enumerate all recursive functions, right? We assume that we can enumerate all recursive functions with using the index e of the function, right? So each function has associated index e, right? And so another way to write this in a very simple way is to say, well, h of x equals phi e of h, the e corresponding to e of h of x, right? It doesn't depend on y again. It depends only on e and x. So if I put e as a parameter of the function here, I can say that h of x equals phi e of x. Okay. And so this e is a number. It's an index. It's unique associated with the function. So we could say, well, basically for each function, whether it's x, h, g, h1, h2, any recursive function, for any recursive function, I'm going to have an associated phi function with an index. So I could really literally enumerate, if I map these indexes that are unique to natural numbers, right? If I index the indexes, if you want, I could really start enumerating them, right? F1, phi1, sorry, phi2, phi3, okay? And so, so now I have my index, and I'm just saying, well, this is the phi enumerates all recursive functions, right? So that's my assumption, and by contradiction, I'm going to show that this is not possible. Some functions cannot belong to this set of countable recursive functions. So I'm defining a function, a recursive function, as phi x of x plus 1. Phi x of x, what does it mean? Well, that's kind of strange, but basically I'm saying, well, this function takes as argument its own number, encoding number. So it's a function that has the same argument as its encoding number. It's kind of strange. Why? Because you could say, what's the relationship, right? There is no link between the encoding number and an argument usually, right? You don't apply s to 1 because 1 is the code for s, right? It's really like saying that g of x. So, for instance, let's say that 1 is the code for s. So g of 1 would be phi 1 of 1 plus 1. If 1 is the code for s, is going to be S, right? If it's a code for S, it's going to select S of 1 plus 1. It's going to be 2. But it's a bit arbitrary that you have the possibility only to have here the same number, right? Because the argument, why would you apply S only to 1 just because the code of S is 1? The code, again, is something very arbitrary too. But we assume that that's what we do, right? And G of 2 is going to be phi2 of 2 plus 1. G of 3 is going to be phi3 of 3 plus 1. And this is going, phi2 of 2 is going to be another function. So in our thing, the phi2, for instance, is going to be the projection. So you're going to project on 2, so you're going to get 2 plus 1 is going to be 3, etc. So anyway, just for the sake of understanding, okay, how it works. It's a strange function, but who cares? You can write, you can define it. And it looks like G is a recursive function, right? I mean, G of x can be also defined as S phi x of x, right? It's a successor of phi x of x. So no problem so far. And the assumption we made, right, is that we can have this enumeration. Well, actually, we didn't make the assumption yet. We didn't make the assumption yet. We are now making the assumption. We're not making the assumption that, well, for each recursive function, there is necessarily, because we can enumerate them, there is necessarily one phi that corresponds to this recursive function. We already said that, right? So the same way that for h of x there is a phi e of x, there should be one also for g, the one I just created. So what is the phi corresponding to g, right? It's phi eg of x, right? So I can then say that phi eg of x equals, I'm going to use a plus 1 notation. Okay. And I'm just going to write e for, eg. I can keep eg, but let's just write it e for simplicity. Okay, so that's the number e is associated with g. And there has to be one because it's a recursive function. Well, and that's the assumption, is that it's a recursive function and they are all enumerable. Well, here we have a problem, and this is where we use diagonalization. It should remind you of diagonalization in the decidability chapter, is that if I apply now f of e, phi of e to e itself, what do I have? Well, I have phi e of e equals phi e of e plus 1, which is a contradiction, right? So therefore, we cannot say that there is an enumerable set of all recursive functions. There is no function, let's put it differently, there is no function phi that enumerates all recursive functions. So there is such a thing as a function that is computable, but not a recursive function, right? So I can compute that function and actually fairly easily understand it, but I cannot find associate it with a phi, a number, a coding number, and a phi according to this normal form. So anyway, I know it's a lot, and it's very very complex in many ways, but I want you to see the parallel between this and Turing machines. And if at least you get a sense of how these work together, how you can make the connection between Turing recognizable and recursively enumerable and decidable and recursive. That is huge. So just to make the parallel with what we saw before, you remember we said that in the diagonalization process, you always have some kind of double self-applicability and negation, right? Just like when we said the set of all sets that don't belong to themselves. So we have an application, a self-application, a negation, and another self-application. That's kind of the order of the process every time. Here, the first self-application is this. You apply phi of x to x, right? So you use the number, the index of the function as the argument. That's the first application. The negation is truly this, plus 1. You do not have identity, right? If I remove the plus 1, there's no problem because phi of e equals phi of e, that's fine. The plus 1 is really the negation, right? And then the second self-application is when I choose to replace x by e here. I do another self-application here, right? So first self-application, negation, second self-application, and that leads to contradiction, which is the same, always the same paradigm in all the theorems of limitation, whether it's for Turing machines, incompleteness, Russell's paradox, or the countability, uncountability of the non-countability of real numbers. Okay, so so that's the idea. I hope this kind of makes sense, and if it doesn't, please don't hesitate to come ask questions. But more importantly, I would refer to the notes that have very extensive explanations of computational trees, and also the whole encoding process. The encoding process should convince you that this is not just pure idea. There is really concretely the possibility to treat a function as a number, and using t, the predicate t, to connect this number to the arguments of the function and to the whole computational tree of the function y. Okay, and I hope also it helps understand a bit the point of unbounded minimization and the power it adds. You could not get this theorem and these results and this capacity to express a function as a number without the unbounded minimization, because you would not have the capacity to search for the right computational tree, for the one computational tree that you want to select. And this kind of searching capacity, you have it only because of unbounded minimization, right? So it's really, you can make so many link with Turing machines, right? At some point, the capacity of a machine to read another machine is made possible by this kind of encoding mechanism, and this is what we have here.